Thank you, Dan. I always love going after Karen because for everyone keeps asking what the future is. It all depends on what you're looking at. It's clear that if you ask what's the most fundamental stuff, materials, then we come devices, and then systems. Okay, but this talk is going to be constrained by what can you build with stuff you can buy. Okay, it's not, and it's a very, very good contrast to stuff that you could build systems with future devices. Okay, and that's where the word practical comes in. So basically, the outline is lots of mistakes over many years. So we learned a lot trying to build systems with real stuff, and that informed us on how to build the next system. And then we learned from that, and we continue to do that. And there's actually a paper on experience track, which is the culmination of our work over many years that George Porter will be presenting on Tuesday. But basically, what kind of OCS technology are you going to want? What's the control plane? For people who see my talks, I pretty much hammer on this. The impact of synchronization and transceiver locking, which has always been a problem and will continue to be a problem in the future. Okay, so because this is somewhat historical, we'll start at the beginning, if you will. We've been at this a while. The first system that we built for data centers was Helios. There was precursor work to this at IBM for HPC. And what was that? This used a commercial MEMS. Even back then, you could literally just buy a commercial space switch network. This was a Glimmerglass. The other company at that time was Caliant. And all the control was software-based. So we bought a switch, and we asked, what could you do in a data center with a commercial switch and writing your software? So this is what Helios looked like. It was a commercial switch. That's this one right here from Glimmerglass. About 12 millisecond switching time. People might have heard elephant and mice. This was designed for telecom grade optics. And the target was interpod. This switch is notable because it really was the precursor system. One of the investigators, Amin Vedad, eventually went to Google, and they actually started developing OCS technology, which for their own internal applications, which they announced a few years ago. Next, we started looking at wavelength switching. We figured, hey, millisecond, no problem. Let's just go to a microsecond because we can find switch technology that's 1,000 times faster. This is great. We're good to go. So this was Mordia. This was a very fast wavelength selective switch made by a company called Nistica. 2 microsecond switching plus some ringing, about 15 microseconds total. And then we say, okay, well, we'll just invent some software to control a reactive network with software at a microsecond timescale. That didn't work out so well. This is what it looked like. It was a ring-based architecture, 24 nodes organized into 6 groups. Each group had 4 servers. This is called a wavelength selective switch. This selected what connections were made at each one of these. It was a ring-based topology. Lots and lots of optics to get it to work. This is what it looked like in practice, 24 servers. Lots of those things on the top are optical amplifiers, optical spectrum analyzers, just a lot of optical hardware to get it to work. So what did we learn from these 2 systems? Well, even back then, transceiver initialization was already an issue. Helios would not have functioned if not for the good graces of a former student that actually gave us the SDK to the physical layer chip that allowed us to turn off some equalization. That equalization was taking nearly a second to converge, and that would have killed us. The switch was a programmable switch, and George Porter actually had to go through the firmware, and he found a wait to state in the firmware that said, even after everything was set up, it waited 2 seconds to actually initialize the connection up to the stack. George commented that out, and we were good to go. No lie. That's exactly what happened. Why am I telling you this? These are going to come up over and over again as you try to build systems with commercial devices that were not designed for the intended application. The biggest thing we actually learned, though, was, and this carried on to Google, was that software control was viable at millisecond timescales. Okay? You can control optical switches at millisecond timescales with software. Mordia system is very fast, but very lossy. And this is characteristic of all, to my knowledge, All switches that used what are called wavelength selective switches, because in the heart of a wavelength selective switch is a splitter. You take a loss and you have to overcome that loss, typically with some form of optical gain. We had 6 optical amplifiers in Mordia, lots and lots of gain. So because of that, that was our last wavelength selected system. We did not think that this could scale. That may change in the future, but again, this was maybe 8 or 9 years ago. And the other thing we learned is software control, at least our initial software control, was not viable at microsecond timescales. So what did we do? Well, we were very fortunate that George Porter on the CS side and us on the hardware side, the CS people spent a lot of time trying to get software to run at a microsecond timescale, okay? And that was 2 system level papers, Reactor and Solstice. And the lessons learned is that's really, really hard. We threw everything but the kitchen sink. We did priority flow control. We tried to do what's called kernel bypass. It's just hard. It's very hard to get software to react at microsecond timescales. And centralized scheduling does not scale well. Shock of shocks, the internet scaled because of decentralized control. Again, we were stupid enough at that time to think we could do this. Centralized scheduling does not scale. Okay. So what did we do? Well, we tried to learn from our lessons. The first lesson we learned is we were going to have to build hardware control. So we started a project which took a very long time, which is basically not software control for the control plane, but actually hardware, a hardware control plane for our future systems. Those future systems consist of a set of 3 projects culminating in the project that will be presented at SIGCOMM by George on Tuesday. The first one was what we call a simple control plane. This is the original reactor, which was, to my knowledge, the first optical discussion of a demand oblivious network. That was in SIGCOMM 17. It was the algorithm for that was, for people familiar with systems, it was store and forward. But that had issues in terms of how fast you could actually send the packets. In some sense, a breakthrough was George Maximelic, and I think Alex figured out a way of doing what's called cut through with an opera protocol, which I'll go over. And then finally, this paper, which will be presented on Tuesday, which is the practical realization of RotorNet. I'll talk a little bit about that, but if you're really interested in that practical implementation, please see that talk on Tuesday. So for people who aren't familiar with rotor switching, I'll very briefly go through this in 2 slides. This is what a typical switch looks like. Packets come in, the packets are read, and a schedule is set. Now, because it's a crossbar, that crossbar actually has n factorial settings or matchings that it could implement. And what happens is it reads the packet headers and it decides which one of those n factorial matchings it wants, and it picks them. So this is just an animation of it picking a matching as it goes through time, reading the information off the packet header. We can't store optics. We can't store photons. We cannot make local decisions, at least not yet, in an in-band network. Lots of people talked about out-of-band, but in-band, no way to read those. Well, let's put it this way. There has been some work on that. That was not very successful, but practically you can't do that. So what do? We don't do it. We don't pick our matching. We cycle through a fixed set of matchings. That's it. So here's an example of n matchings. These are matchings. We call them matchings. Maybe a better word is changes in topology of the network. So you hear a session in SIGCOMM called reconfigurable topologies. This is literally changing the connection pattern between endpoints on a network. And there's no central control. We're not trying to read packet. We're not trying to look at data, extract a demand matrix out of it, factor demand matrix, and set up a control. It's just, this is what you get, figure out how to deal with it. So that's comparison to electrical switching. In comparison to optical switching, so you've heard about MEMS cross connects. That was what was used in Helios. In a typical MEMS cross connect or a typical, it's just an optical crossbar. One input port is matched to one output port. And again, you have n factorial settings. So each one of those input ports can go to any one of the n output ports. In the rotor topology, it's actually what's called a gang switch. So all the inputs come in and all the inputs go to one specific matching, which sets the topology. So this is actually the secret sauce of why we can decouple it. I'll go through that in a bit. But basically, all of the inputs go to a matching. That matching controls the input-output configuration. So why is this so useful? In terms of cost and complexity, a typical cross-connect will go as a number of ports. But really, the most expensive part of a rotor switch is the number of matchings. We pay for that because while the switching speed typically goes as a number of ports for a typical cross-connect, it goes as 1 over the number of matchings. So we actually lose speed, and we have to figure out a way of speeding that up. And this was the key idea behind Opera. The idea here is we're going to trade limited conductivity versus switching scaling. So how do we get this thing to run faster and not have latency? What you're seeing here are endpoints. Each one of these endpoints is not connected to a single rotor, which I'll show in a second how that's actually physically implemented. It's connected in this case to 3. Now, if I didn't do anything, all of these optical switches are going to have a dead time shown here where I can't send any information. And that's an inherent latency that I can't get around. So what do? The key idea for Opera is don't change the configurations of each one of those 3 rotor switches at the same time. We stagger the switching of each one of those rotors. So in fact, at any given instant of time, there is always a path through the network from a source to a destination. It might not be a direct optical path. In fact, most of the time it's not, but there's always a path where I can take a packet, send it someplace, and immediately turn it around and send it out. So that this gets around the latency problem of actually waiting for your connection. The other thing that multiple rotors do is I have to cycle through all those connection patterns. By splitting them up between multiple rotors, I actually can make that cycling time much, much shorter. So this was actually a big deal. And what this does is each of these rotors, this is now an example with 4 rotors as opposed to 3. Each of those rotors goes through 4 configurations. So those 4 configurations for each of the rotors are shown in colors on each one of these curves, on each one of these partial diagrams. So if you just overlaid all 4 of those matchings, the 4 matchings that each one of the rotors implements in one full cycle, they cover the full graph, meaning that this 4 rotor system can switch anywhere, it's fully connected, okay? Even though each one of the rotors by themselves is not. So this is a classic example of taking a limitation for a single device and through clever systems engineering, making a more complete system. And George Porter will talk more about that later on. So this is 4 rotors with 4 matchings, provides full connectivity. Okay, physically, this is how it's done. There's a lot of people here who don't know the optics, so I'll just briefly go through it. This is a commercial, does this work? Where's the, is that one? Which one? Oh, the other one.
But it's invisible to the screen.
Okay.
You can see it, but it's invisible.
Okay, you know what, I'm just gonna use my hand. Old school. So this you buy, this is actually in every single MEMS switch. This is 20-year-old technology. So it's called a micro lens array. The red lines are the forward direction. So that's the input. The blue lines are the output. The system is, there's a fold mirror, which sends it to diffraction grating. The diffraction grating actually selects one of these 4, in our case, one of these 4 matchings. The matchings are actually implemented in previous systems. We actually used fiber arrays, physically connected them. A huge practical change was we actually had microprism reflectors fabricated, and this is actually a commercial, low-cost way of making these connection patterns. The details of this were presented at the Optical Fiber Conference earlier this year. But basically what we have is we literally have a spinning disk. It has 4 different diffraction gratings. Each one of those diffraction gratings picks a different connection pattern. So the way to visualize this from a systems perspective is this is producing a periodic change in the topology of the network. And that periodicity, the change in that periodicity depends on how fast that disk is spinning and some details on how the switch is put together. So by doing that, the diffraction grating picks the matching or the topology. The routing is done by these microprisms, and by decoupling those, that's how we can take a limited conductivity system and create a fully connected system. This is what it physically looks like. Max Millet designed it. As I said, this technology is commercial. You buy it. That long tube is actually to demagnify. This is the input fiber right here. Notice that it's not square. There's a reason for that. And that whole fiber array is imaged onto that diffraction grating. It's actually demagnified. And this is what it looks like. That square up top, those sectors are, each of those sectors is a diffraction grating. That entire sector sits on one of the entire, excuse me, the fiber array sits on one of those sectors. And as the sectors move, because the disk is spinning, that whole array goes from one sector to the other. And by shifting from one sector to the other, it creates a different matching. That's what it looks like. Because we're using basically literally hard disk technology that can spin very quickly, the switching speed of this is 7 microseconds, worst case, and half a microsecond, best case. So this is actually much, much faster, about 3 orders of magnitude faster than a commercial MEMS switch. This is what it looks like in practice. I'm just, this is the switch inside the rack, back of the switch, lots of fiber, lots of connections. Yeah, but that's where all the measurements were made. So why do we build it that way? So that's what we built. From a systems perspective, why? And the answer really has to do with understanding what we're trying to do with systems. In optics, one of the big advantages of optics is it's actually, if you build it correctly, it's transparent to the type of modulation format because it's just a pipe. So we'd like our optical switch and system to be transparent with respect to modulation format. And of course, we'd like it to go fast. So we capture those things in terms of 2 types of transparencies. The logical transparency is basically how quick the entire network switches, which I'm going to get back to. And then physical transparency, which is basically how transparent it is to different modulation formats and rates. So if you look at standard types of switch technology, SOA stands for semiconductor optical amplifier, tunable laser, and AWGRs, that's a special type of passive grating that routes wavelengths to output ports. MEMS we've talked about, and then the rotor switch. The rotor switch really was designed to balance logical transparency and physical transparency. It was designed to go fast as we could, but still maintain the ability to basically to be rate agnostic. And that's really the focus of that. Once we've made that decision, then you have to ask, well, what kind of switch do you want to build? And there's several kinds. We built obviously spinning diffraction gratings and so on. We built a free space, 3-dimensional switch. And this wasn't rocket science to us because all commercial switches, all underscore, that means space switches like MEMS, or even wavelength selective switches, which are used in wide area networks, use free space designs. Particularly for space switching, which is what we're doing, a very special kind of space switching. It has high physical transparency because it's just mirrors, port count and loss. In other words, we get lots of ports, relatively low loss, and it's rate agnostic. These are great things. But the problem with most other types of space switching technology is they're slow. And that's really what we focused on with the rotor systems. Planar 2T switches, they're faster. You can get nanosecond switching. The figure on the right is from our lab of a test chip from IBM that switched in nanoseconds. The problem is physical transparency. So these waveguide devices tend to worry about polarization, and there's lots and lots of fibers. So that fiber array that we had, that's commercial technology that's been around for over 20 years. If you want to build a planar optical switch, say 128 port by 128 port, which is what we built for RotorNet, you would need 256 fiber connections to that chip. There's nothing physical there. It's just a practical thing of connecting 256 fibers, yielding, and so on. So they tend to have lower radix. As Karen commented, the switch they're looking at might be 1632, maybe 64. They tend to have high insertion loss because of this issue of coming into a fiber into a rectangular waveguide and assembly cost. So for all these reasons, commercial switches tend to be free space. And then, who knows who knows about the future, but that's kind of what we went with because again, of the practical constraints that we impose upon ourselves. So I'm just going to speak about three things about the RotaNet architecture. George will talk more about this later. The blue area is what our FPGA NIC handled, and I'm going to be talking about host-host synchronization. The light green area is how we coordinated the spinning of that spinning diffraction grating with the emission control. And the pink area is the optical switch. So I'll just say a few words about that. Remember I said all the way back in Mordia? That was 2013. We're showing this paper in 2024. This took an enormous amount of effort. Anyone who's assistant professor trying to get tenure, do not do this. Okay, this took a long, long time. It was the singular focus of a very, very special individual who got this to work, Alex Ferencic. But it did everything. It does all the things that we need to be able to synchronize when we inject the packets into the network and how the disk spun. Particularly, we know that we had custom, you have to have some form of hardware at microseconds. You can't do everything in software. It's just I don't believe that. You show me the paper, I'll ask some very hard questions. Maybe you can do that. We use a standard protocol. It's called precision time protocol. We got less than 1 microsecond over a 16-node network. That was fine for what we needed. The other thing is, if you really want to do this, you tend not to want this. This was host-host networking, so there was no TORs, there were no switches per se. You want to keep everything really, really close to the wire. Having a data transfer come in, go down the PCI network, access memory, and come back again, not so good. So the Opera protocol, the packets never left the FPGA. They got turned around in the FPGA. The host wasn't doing anything and turned right back around. Okay, so host rotor synchronization, another problem, you got a spinning disk. You got a computer. You had better inject those packets when that disk wants to be injected. How do you do that? We had to build our own control board. We had to develop a feedback signal based on PCB time. This is what the control loop looked like. Eventually it converged to 5 microseconds. You go, well, that's not great. You got a microsecond for PTP time. You got 5 microseconds. But believe it or not, this is not the limiting system level thing to get the network to work. The limiting is this. So this is kind of a busy chart. I'm going to kind of go through this. So when the switch is switching, obviously you can't send data. Even after the switch changes its transition, going from that one sector to the other, that's that red line. Once you're in that new sector, the transceiver has to figure out what's going on because it's a different connection. It's a different transceiver, different power level, different clock phase. So this yellow area in all these things, lock time, lock time, lock time, lock time, that is the time it takes the transceiver to figure it out. So yellow is bad. That was blue, but purple is good. So the band of yellow is telling me how long it takes to lock. It depends on the different power levels, the offset of the power level. In other words, if I'm going from high to low or low to high, it also depends on the speed. So if you look at 10 gigabit per second operation and 25 gigabit per second operation, you can see that 25 gigabits, it takes longer. Okay. So this is not specified in any standard. We literally bought every single commercial module in the market and characterized them to find the one that worked the best. I'm happy to tell you what it is, but because we use these things, this gets back to what we learned in Helios, because we use this thing in non-standard, it was a huge problem. So multiple lock time, a module takes a data rate, absolute power, and transition. And for us, if you take a look at it, the switching time, 7 microseconds. The lock time is another 20 microseconds about. So between the switch and the lock time, I'm at 30 microseconds. The 5 microseconds for jitter, okay, it's not great, but it's not the one that's killing me. And the PTP time of less than a microsecond, I don't care. And this is incredibly important for people building systems. You can't just focus on one thing, okay? Because you won't get it to work. And in our case, it's the transceivers that are causing the problem, not the physical switch time, not the synchronization, not even the jitter of controlling the coordination of our disk with the computer. So as I said, the main reason is this type of operation where the signal goes down and comes back up is called burst mode operation. Transceivers, commercial transceivers are not designed for this. We heard about PON this morning. PON is a burst mode system. It's not like this technology doesn't exist. It just doesn't exist in the data center context within the standards. The other issue is that we use these things at 10 and 25. That's almost ancient history in data centers. As you speed up, and particularly as you switch from NRZ, non-return to zero, to more complicated formats like PAM4, it gets a lot more complicated. The transceivers have a lot more things going on. These are all the things that happen. So 10 to 25 turns out to be actually a pretty sweet spot. And to give you an idea of just how bad this is, if you just go to Xilinx, Xilinx is a company that builds FPGA boards, and they build their own transceivers, and they'll report on the acquisition time of different types of protocols. So a standard protocol that they use, 25 gigabit per second NRZ, takes about a millisecond and a half, which is still slow, but at least it's manageable. The same company building a GTM transceiver, which is a PAM4 transceiver, 1 second. Almost 3 orders of magnitude longer, okay? Transceivers were a problem with Helios, and 15 years later, they are still a problem. It is not fundamental. There's designs for burst mode PAM4, okay? Not fundamental, but if you don't have that technology, you're not going to be able to build a system, okay? So our experience is we're trying to balance the ability of optics to be almost future-proof in terms of physical transparency and logical transparency in terms of how fast we go. That's what drove RotorNet. Methods that require significant transceiver power, optical amplifier are expensive, both from a cost and energy, and are currently not implemented at scale. Lots and lots of papers on planar stuff with wavelength. That may change, but right now, I know of no system at scale that's using that technology. The biggest issue is fast microsecond control planes require significant hardware support. You're not going to do this in software. We learned that after about 4 years. If you're at microsecond, existing standards are probably good enough. I don't think you need to invent a new synchronization standard. I think PTP is fine until we're really pushing sub-microsecond. And we've got all kinds of other issues to even get to a microsecond before we push to sub-microsecond. And finally, commercial transceivers, it's a practical issue. It was a practical issue 15 years ago. It's a practical issue today. That, to me, is still the issue. It's great that Google announced that they've got commercial OCSs, but until this happens, it's going to be very, very difficult for other vendors or other people to put together systems because you can't buy the technology you need. If you bench up a standard PSM4 right now, it's about a second. That's death. Okay. So acknowledgements. We have been very, very fortunate to be pretty well funded, and very fortunate that hardware and software people have been working together for a very long time. George Porter and I have been working on this for a long, long time. Lots of UCSD collaborators, postdocs. 2 people mentioned, Max Millett is mentioned 3 places, graduate student, postdoc, and external collaborator because he started his own company. And Alex Ferencic started as an undergrad, actually built a lot of the Mortier hardware as an undergrad, grad, and then postdoc. And it was his stubbornness that basically got Corundum off the ground. So I'd like to say that this was something that we did, but really the students just put it together and got it to work. So thank you.
You have a question now? Okay. Me? Okay, thank you. Very great talk. So I have 2 questions. The first one is, are the router switches programmable? I mean, if I want a different set of matchings.
No. Once you fix those, once you stamp out that pattern, it's stuck for now. Okay, but everything that we presented, that's what you get. Okay. So it turns out that all those patterns are expander graphs, if you know what those are. So they're actually very flexible, but they're fixed.
The second question is, now the link speed in data center is higher and higher.
Yep.
Do you think it's more like a challenge or more like a chance for this traffic of previous of data center?
Well, I think I think I'm going to leave that to the experts in demand oblivious who are actually in the audience. But I do think that I do think that demand oblivious is a very, very interesting thing, whether or not it wins out. If for optics, it's particularly important because we can't get local information at the switches, right? This is the key insight, right? Since we can't process packet headers, right? Other people may argue, but I think the future of optical switching is almost going to have to be demand oblivious because of that fundamental fact. Okay.
Thank you.
So what's the maximum stability of this filter network?
Great question. So with respect to ports, if you want to, you can just keep demagnifying. We didn't even push the limit of demagnification. I mean, literally, we could go to 1,000 ports with very little change in the basic technology. Now, if you're asking the number of matchings, that's a whole different question. Because the matchings require different diffraction gratings that go off at different angles, and those have to propagate through the optics. That's a much harder problem. So in terms of total number of ports, believe it or not, relatively easy. In terms of number of matchings, harder problem, not impossible, but harder because the optics design gets harder. Okay?
So what I mean is, what about the stability of the entire network? The entire data you are building optical data system network?
Sure. So I could wire up 1,000 hosts with this.
Just 1,000 hosts, I think.
Well, that's one level. I mean, just 1,000. I know of no two-level network that's at 1,000 hosts. So I think so. Yes, I mean, yes, I know. Yes. So the simple answer is now you're asking about cascading optical switches, and I would answer the question is how much loss can my link budget tolerate?
So I'm asking about we have so many top of rack switches and
There's no top of rack switcher, none. This goes straight to the host. This is host networking. So we could, I mean, we haven't talked about it. Maybe George can talk about it. It is conceivable that as opposed to putting it at the host, we could put it at the switch, but that's going to require a lot more intelligence in the switch than is currently possible with existing technology. So if you allow me to have arbitrary functionality at the switch, sure, I can do this. Okay. But now all this synchronization